a pre-calc trig class. But if you haven't, this will be new, but it's actually really nice. So remember, what we've done in chapter 6 is counting, and using combinations, permutations, and in a sense, that's all the binomial theorem is. I'm not going to prove it. The proof should be in your book if you want to look through it. But it's useful for things like this. So expanding x plus y to the third power. So this one, isn't bad if we wanted to do it ourselves, right? X plus y to the third is x plus y times x plus y times x plus y, right? And you can multiply all that out, FOIL the first two, and then distribute that last term in there. Right, but you do all that and you get x to the third plus 3x squared y plus 3xy squared plus y cubed. Okay, so if you wanted to do all that, you could. The binomial theorem is actually going to give us a short way of expanding things. Okay, so binomial theorem, so we got x plus y to the nth power. Okay, which is what we had above, right? You have an x plus y, in this case, to the third power. Okay, so we're going from j equals 0 to n. Okay, so n above is 3, right? Is n equals 3. And it's the summation of all these terms, all the terms where we are looking at this right here. Okay, remember this notation there is the same as n choose j, all right, combination. It's just a different notation for it. Okay, so if you look at applying this to this first one that we just did, right? So we would start at j equals 0. Okay, so that would be, this first one would be, so we're going 3, choose 0, x to the n is 3 minus j is 0, and then y to the 0 power, right? That would be the first term, right? Plus the next one, right? The next one now is, we started at 0, so we're going to 1. So 3, choose 1, x to the 3 minus 1, j to the first power, or y to the first power, j is 1. Okay, move to the second one, you get 3, choose 2, x to the 3 minus 2, y squared. And the last one is 3, choose 3, you get x to the 3 minus 3, y to the third power. Okay, and those four are the same terms that we had above. Okay, now you don't have to do these by hand. If these numbers aren't too bad, but we'll get to bigger numbers. You have combinations and permutations in your calculator. So if you take out your graphing calculator, I might have told you guys this before. If you hit math, so the third one down on the first column, you go over to PRB, which is probability. It'll be the third one on there. So let me write that. So in your calculator, you go math, you go over to PRB, and then you go down to the second one is combination, the third one is, or the second one is permutation, the third one is combination. So you go down to number 3, which is NCR. Okay, so you would actually have to type in your N first, and then do that one, and then whatever your R is. Okay, but those will give you all your coefficients that you would need. right? These numbers aren't bad. You can, I mean, we can do these by hand, right? 3 choose 0, we know is 1. 3 choose 1, 3 ways to do that. 3 choose 2, 3 ways to do that. And 3 choose 3, 1 way to do that. All right, so why don't you guys take a minute and do it to x plus y to the 4th power. All right, so use binomial theorem and expand x plus y to the 4th power. All right, so binomial theorem. So applying this, right? The first one we'll have is we're going up to 4, so we got a 4 choose 0. All right, and this will be x to the 4 minus 0 power, y to the 0 power. The next one is 4 choose 1. You got x to the 4 minus 1 power, y to the 1st power. And we get a plus 4 choose 2, x to the 4 minus 2, and then y squared, plus 4 choose 3, x to the 4 minus 3rd, y to the 3rd. And the last one, 4 choose 4, x to the 4 minus 4, y to the 4th power. All right, so 4 choose 0 is 1. So that first one is just going to be x to the 4th, since y to the 0 is 1 also. Plus 4 choose 1 is 4. You got x to the 4 minus 1, so x cubed, and then y to the 1st, plus 4 choose 2 is 6. X squared, y squared, plus 4 choose 3 is also 4. And that is x to the 1st power now, y cubed, plus 4 choose 4 is 1, x to the 4 minus 4 is 0, so that's 1, y to the 4th.
I have a question.
Yeah.
So I got like everything good, but except the coefficients in front of the variables, like the 4, the 6, and the 4. I completely skipped that part.
Okay. Well, those are choosing ones. So like I wrote up here, the nj is like combination of n choose j. So that was like from last class. So remember, you can do the formula. It's the n factorial over j factorial n minus j factorial. It's that formula. I mean, you can just use your calculator now. You don't have to. You don't have to do all that work. So the calculator is this one here that I have above. But that's that notation. Is that your question?
So how we got the 6?
The 6 is this one. 4 choose 2.
Oh, I see. Now I got it. Thank you.
Yeah. Okay. Cool.
Just to verify for the exam, because you said we can use the calculator for the combinations, we don't need to show work for that, right?
No, even for your exam on this one, if I'm asking you to like count stuff, you can just leave it in this form. You don't even have to plug it into your calculator.
Okay.
I actually prefer just this rather than the calculator one, because it's one of those things where, like, if you plug it into your calculator, but let's say you did combination instead of permutation in your calculator and you got it wrong, at least I have the work on there for me to give you partial on that. So I would say just leave it in this form. The only reason we're multiplying it out now is because of those. We wanted like coefficients.
Okay. Very good. Thank you.
Yeah. Mm-hmm. Any other questions? All right, so let's look at this one. So a little bit different type, not just expanding. But what is the coefficient of x to the 12th power, y to the 13th power in the expression x plus y to the 25th power? Okay, so don't really want to multiply all these out or add all these up, right? But let's just think about what term that would be, right? Where would that fall in there?
So couldn't you find that by doing 12 factorial divided by 12 factorial times, well, just using the n factorial, j factorial times n minus
exactly.
j factorial?
Yeah, so that's exactly what you want to use, right? So we have this x to the 12th, y to the 13th power, right? You can kind of think about, well, where does that 12, where does that 13 come from, right? Well, we know these coefficients are coming from these choosing parts, right? And these choosing parts are coming from n choose j, right? Well, in this case, n is my 25, right? And you're choosing, right, that j. Now that j in this case would be, well, if we want, I'm matching it up with what we have up here, what I boxed, right? J is coming from that thing on the y, right? That exponent on the y variable, right? So in this case, it would be the 13. Right? 25 choose 13, just matching everything up with what we have above. All right, is there any questions on where that 13 came from, the 25? All right, so you can plug this into your calculator, right? So you can do all that. But Joseph was saying this is also the formula. 13 factorial, 25 minus 13 factorial. This is a pretty big number.
It's 5,200,300.
200,000. Thank you. 300. All right, so that would be the coefficient of that term. All right, and just use your calculator for that one. All right, any questions on that one?
So for the test, are we gonna Do you want us to plug it in the calculator and give you the final result, or do you want to just like the 25 factorial and 13 factorial and just leave like that?
So for this test, you're not gonna have this section on there, right? So far, this is like the only section where we've multiplied things out, because we're actually asking for what the coefficients are. But for like the other sections where you're just counting things, you can just leave it in these forms. You can leave it in that form or in that form.
Okay, for sure.
Yeah, for a lot of these, I mean, unless it's like expanding like this, where we want to see those numbers. I don't care too much about that final answer, because I mean, all you're thinking is coming from these, right? So yeah, and then on your test, I'll say you can leave it in, I'll say combination or permutation form or factorial form. All right, so let's do one more. Okay, so what is the coefficient of x to the fifth, y to the third, and the expansion of 2x minus y to the eighth power? So a little bit different now, because we don't just have the x plus y in there, right? The other ones we've done were all x plus y, right? X plus y. Now you have a 2x minus y, right? Now binomial theorem still works. It still holds for things like this. Now you got to think about it a little bit differently, right? But it's still going to work. Okay, I mean, if you want, you can rewrite this as 2x plus negative y to the eighth power. That way you have it in addition form, right? Because that negative is going to change signs, right? Every time you multiply by, another negative y, it's changing the sign. So that negative definitely comes into play. That 2 is also coming into play, right? Because if you just kind of mentally think about if you were to, you definitely don't want to, but multiplying 8 of these out, every time you do a 2x times another 2x, it's changing, right? So this is still going to work the same way, right? So I'm looking at x to the fifth, y to the third. Okay, x to the fifth, y to the third. So let's write this. Remember, we had n choose j, right? So n was, what are we going up to? In this case, our n is that 8. Right? J was the exponent on the second one, so in this case the y. So in this one we're looking to the third power. Okay, now the thing you have to be careful of is that choosing right there is not accounting for that 2 on the x and that negative on the y, right? Because if you think about what this term actually would look like, using if you were to write all this out, it would start off with 8 choose 3, right? But you would have 2x raised to the, in this case, x is to the fifth power, and a negative y raised to the third power. All right, so if you did your binomial theorem without even, asking about x to the fifth, y to the third, that is what you would have when you write it out. Now it simplifies and you get the x to the fifth and that y to the third in there. You see that now the 2 is coming into play and that negative 1 is coming into play. All right, so what's 8 choose 3? 50, is that 56? I think it's 56. 56 from the 8 choose 3. And you get a 2 to the fifth, x to the fifth. All right, rules of exponents. And you get a negative 1 to the third and a y to the third.
I have a question.
Yeah.
Isn't the x to the fifth and the y to the third accounted for in the 56 when we do the initial combination.
So that is the coefficient if it was just x and y, right? Because you see how like when we did the 8 and the 3, in there you don't account for anything of the coefficients already with them, which in this case is like the 2 and the negative, right? All we used was the exponents. So this is just coming from the exponents, right? But we got to account for that 2 and that negative, which is where this is where they come into play here.
Okay, I got you.
Okay, so you get a 56. 2 to the 5th is 32. So 56 times 32. This will be negative because negative 1 to the 3rd is negative. 56 times 32, 1792. And then you get x to the 5th, y to the 3rd. So that coefficient then is negative 1792. Yeah, cool. Thanks, Willie. Any questions on that one? All right, cool. So we have some corollaries here. Some corollaries are just smaller theorems. The only one I want to prove is this first one because it kind of ties back to what we did a while ago. So n is a non-negative integer. Then the summation from k equals 0 to n of n choose k is 2 to the nth power. All right, and we're gonna kind of do like I don't know how much of a, direct proof this is kind of just tying it to what we did a while ago. So let's think about a set with n elements. Okay, so we have a set with an n number of elements. Okay, now think back. How many subsets are there of a set with n elements? Yeah, it's 2 to the nth power, okay? So there are 2 to the nth subsets. Okay, because remember for each element, the way we got that 2 was we can pick that element to be in the set or we don't choose it to be in that subset, right? So each element has 2 options. It's either in that subset or it's not, right? So you get 2 options for the first element, 2 options for the second one, 2 for the third, and then so on. So you get 2 times 2 times 2 n number of times. So you get 2 to the nth. Okay, so each subset then has 0 elements, right? You can have the empty set, 1 element, 2 elements, right? All the way up to the set itself of n elements. Okay, so you can choose these, right? So, I mean, there's going to be n choose 0 subsets with no elements, right? That's how many ways to choose. So if you have a list of things, you're choosing 0 of them. There's only one way to do that, right? N choose 0 is 1, right? You know there's only one empty set, right? It's the thing with nothing in there. Right? There's going to be n choose 1 ways or subsets, right, with one element. And you'll start to see the pattern. There's n choose 2 subsets with 2 elements, right? All the way up to n choose n subsets with n elements, right? All those together are your number of subsets, right? But we said that there were 2 to the nth of them. So adding all these together should give you 2 to the nth, which is what that corollary is. Right, so kind of like an indirect way to think about this, but it's kind of nice putting things that we've talked about before together with new things. All right, any questions? All right, cool. So there's a couple other corollaries in there. I think the proofs of these are in your text, so if you want to look at those, they're not really going to come up. You do them the same way that you would with any summations. You can just add them up. Yeah. The last thing I want to talk about in this chapter is Pascal's triangle, which, maybe you've seen this, maybe you haven't. I'm going to try to make this as nice as I possibly can. The way I did on my paper is a mess. So Pascal's triangle is, I think I'm already, so it starts to look like this. So you kind of start off with these ones, all right? And you always start and end a line with a 1. And to get these terms in here, you add those. So the 1 plus 1 would give you the 2, right? And you kind of end with a 1 in there, right? And these lines start to get longer and longer because you start to add more and more things together. Okay, so I start with a 1. Right? I'm going to get that 1 plus 2, which is going to give me a 3. I'm going to get a 2 plus 1, which is going to give me a 3, and then end with that 1. Now, you don't need to prove all the corollaries. There was 3 corollaries, but I just wanted to show that one. The other 2 are just, they were in your text, so I put them in there, but they're not really going to come up. To get the next line, so we start off with the 1 again. You get the 1 plus 3, which is 4. You get the 3 plus 3, which is 6. You get the 3 plus 1, which is 4. And you end with a 1. Right? And you can keep on going, right? So you get a 1. You get the 1 plus 4, which is your 5. your 4 plus 6, which is your 10. Your 6 plus 4, you get another 10. And you get the 4 plus 1, which is a 5. And then you end again with a 1. Right, and I'll stop there. Now, this might be familiar, might not be familiar, but it just keeps on going. Right. You might have used this for, maybe expanding things out. Because what you should notice is there's so many patterns in Pascal's triangle that even like the way I drew it on my notes is a mess. So I'm trying to organize it nicer. But this line right here, we actually did that today, right? The 1 3 3 1, that was this one here, right? The coefficients of this 1 3 3 1. Okay. The other thing you should notice is that, okay, we're in the combination permutation section. So how do we relate this? Well, that first one at the very top of that triangle, it's like a 0, choose 0. Right. Now, the second line with the ones, well, the next thing would be 1, choose 0, 1, choose 1. Right. 1, choose 0 is 1, 1, choose 1 is 1. That third line, okay, now moving to 2. So 2, choose 0, 2, choose 1, 2, choose 2. Well, 2, choose 0 is 1. 2, choose 1 is 2. 2, choose 2 is 1. Right, the next one, 3, choose 0, 3, 1, 3, 2, 3, 3. All right, you get those. The next one, 4, 0, 4, 1, 4, 2, 4, 3, 4, 4. Right, and it looks like the coefficients from your binomial theorem. All right, 5, 1, 5, 0, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5. Right, and they're all the same. All right, now there's a bunch of patterns in here. You can look them up. I'm just gonna make a mess if I try to write all these patterns in here, but I mean, you can see some of them. Right, you can see your counting numbers are going down here, right? 1, 2, 3, 4, 5, 6, 7, 8. You just keep on going down. These numbers here, called your triangular numbers. Which is just building triangles. We don't really talk about it too much. What else? Fibonacci is in here. Let me see. I think I need more so you can see that. But yeah, it's in here too. Okay, but I mean, this kind of leads into this identity here at the bottom. The 1 plus, or choosing n plus 1, choosing k from n plus 1 is equal to n choose k minus 1 plus n choose k. Well, remember how we built this one, right? We were just adding the previous ones to get the next one. So I mean, if we look at, an example over here, let me just choose these right here. All right, this 4 choose 1, 4 choose 2, that's like the 4 and the 6. We added those together to get the 10. So 4 choose 1 plus 4 choose 2. Let's see, an example of this. 4 choose 1 plus 4 choose 2. Right, putting those together would give me the 5 choose 2. All right, and that's what that identity is. Now the proof of that isn't too crazy. It's kind of just talking through it. But I mean, I don't want to spend too much time on that proof. But yeah, I just wanted to kind of throw that in there and just give you guys some exposure to that. Are there any questions on Pascal's triangle? So it's just relating the binomial theorem, right? It's the coefficients.
Is that its primary use?
Yeah, I would say that that's like the biggest thing that it comes from. You know, but there's a bunch of I'm going to copy and paste this into the chat. There's this link that, you know, you can see all the patterns from it, and they draw multiple triangles out, so you can see all the patterns. But it's just cool seeing how many things come from this triangle. But yeah, the binomial theorem I think is the biggest one in there. All right. Any other questions? So that's the end of chapter 6. So remember, 6.4 is not on this exam. Okay. Not on this exam. All right, cool. So let's start chapter 7. So I'm thinking we should be able to finish chapter 7 today. It's probability. A lot of this goes by fast because there isn't too much work to all of these. So probability, we have the actual definition there. Now it's exactly what you've always thought probability to be. Okay, so S is a finite, non-empty sample space. Okay, remember, sample space is all your possibilities of equally likely outcomes. And E is an event, a subset of S. An event is a subset of S. Then the probability of E happening, and we use this notation little p and then parentheses of E. So the probability of event E happening is the cardinality of E divided by the cardinality of S. Right, so it's just like, you know, you roll a die, let's say they're all equal. We'll see somewhere they're not all equal. But, you know, if your event is that you want a 6 to come up, right, well, your subset is just 6 because there's only one 6. Right, so how many things are in that event? Well, it's just 1. There's only one 6. Divided by, well, all your possible options, there's 6 things, so 1 over 6. But it's exactly what you thought of probability to be. Okay, now writing it in this form helps you understand, you know, I don't know, we've probably talked about this probably the first day when we did the birthday probabilities. But probabilities have to be between 0 and 1. Right? You can't have a negative probability, and you can't have a probability greater than 1. Right? Between 0 and 100%. Right? You can't have anything greater than 1, which is greater than 100%. right? 100% or 1 means that is for sure to happen. 0 is that it's impossible. Okay, so you can't have anything outside of those. All right, now you can kind of see that, coming into play here, because we're talking about finite, non-empty sample spaces, right? So, I mean, if E is a subset of S, right, E can be empty. Well, if E is empty, the cardinality of E is zero, right? Divided by something that's not empty, it's going to be 0. Okay, so I mean, that's the smallest thing you can get, right? The biggest thing you can get is that E itself is, the entire set S, right? So if E is, right, then you get cardinality of E, cardinality of S. Well, those are the same, right? So you're going to get 1, right? Because remember, E is a subset of S. Right, so just by that definition, it has to be between 0 and 1, right? Can't be anything greater than 1, it can't be anything less than 0. Right, any questions on the definition? Now notice, it says S is a non-empty sample space, right? Because if it ends up being empty, well, the cardinality is 0, and then according to our definition, we're dividing by 0. And we know we always get problems with that. Okay, so S being non-empty is very important. All right, so let's look at this first example. It's pretty nice. So you have a bucket, 5 white balls, 10 black balls. What is P of W? W is the event of picking a white ball. Okay, so the way you think about this is, well, we're looking at fractions, we're looking at the cardinality of E. So E is in this case is W, the event of picking a white ball. Well, there's 5 of those, right? Over the cardinality of S, which is everything. Right, so total, there's 5 white ones, 10 black ones, so there's 15 total, which is 1/3. Right, and with probabilities, you can just leave it as a fraction. You don't have to, divide them or put them as a percent. Fractions are okay. All right, any questions on that one? Start you guys off with something nice. All right, so looking at the next one. So we talked about cards last class. So there are 52 cards. There's 4 different suits, or they're just shapes, right? 4 different shapes. 13 different numbers. So like A, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there's Jack, Queens, and Kings. So 52 total. So we're not including the jokers. Okay. If you're not okay with cards, let me know, because we're going to do a lot of card ones today. Is anyone not okay with cards? I don't want to assume. All right. So you get dealt 5 cards from your 52 card deck. Okay, what is the probability that you get 4 of a kind? So 4 of a kind means that the 4 out of the 5 cards are going to be the same like number, right? So you can get 4 different, or you get 4 jacks. All right, so you get the diamond one, the heart one, the club one, and the spade one. Okay, what is the probability that that happens? Okay, so I'm gonna write out, what we had. So 52 cards. We had 4 suits or shapes. We had 13 of each. I'm gonna just say number. A, Jack, Queen, King aren't numbers, but we'll just call them numbers. Okay, so how do we build this probability? Okay, well, we can do the denominator, right? Remember, the denominator is how many things are in your sample space. So in this case, my sample space is getting dealt 5 cards. How many ways can you be dealt 5 cards? Well, we actually did that a couple sections ago, right? I think we did that in 6.3. We did that right here. Right, how many 5-card poker hands can be dealt from a 52-card deck? We had that combination of 52 choose 5. Okay, so my denominator is 52 choose 5, right? And it was yeah, so it can't be 5 factorial because that's part of it, Willie. And I think it's a little bit smaller than 1 over 13, Karima. Yeah, it's 52 choose 5, because remember how we did that? So we said, this is a good review. These 5 spots are like my 5 cards, right? So for my first spot, I have 52 options. I can get any of the 52 cards. My second one, I can get 51, and then I can get 50, and then 49, and then 48, right? And remember, the problem with that was you're repeating things in there, right? So you have to divide by factorial, which is, I think, what you were thinking about, Willie. But that right there is that formula. Okay, so it's the combination, right? Remember, combination is order doesn't matter, right? So that's where that came from. So that's your total number of ways to just get dealt 5 cards, right? That's the size of your sample space. Okay, what's the probability that you get 4 of a kind? Okay, so how many ways can we get 4 of a kind? All right, so I'm gonna break this up into pieces. Okay, now the first thing we got to choose from is, well, which one of those numbers is gonna be my number that I'm looking at, right? Am I looking at the 2s, the 3s, the 4s, the 5s, the 6s, right? How many ways can we pick one of those cards? Well, there's 13 to choose from, right? And I got to pick one of those, right? That right there is saying, you're picking a card. All right, you got 13 different valued cards to choose from. I want one of those. Okay, times, well, the next thing I got to pick is the suits. All right, well, how many of those suits or shapes do I need? Well, there's 4 to choose from. Right, but if I'm getting 4 of a kind, well, I need all 4 of those, right? I need the hearts, the diamonds, the spades, the clubs. I need all 4 of those. And the reason I'm doing this, 4 choose 4 is 1, so I mean, it doesn't change it, but it's gonna help us write the second one. Okay, the next example. Okay, so you've picked a card, right? You've picked one of the values on the cards. You've picked all 4 suits. What's left to pick? There's one more thing you have to choose. Anybody know what it is? So the shape, Karima, is remember we want all 4 shapes. That's this right here, right? So we picked the shapes. Yeah, it's that, Willie. You need the last card, right? You've only picked 4 cards. You need the last card. Right? So how do I pick the last card? Well, okay, I've used up 4 cards, right? My 4 of a kind. So if I've used up 4, you know, how many cards do I have left to choose from? Yeah, Chris, you're right. All right, you've used the 4, right? So the last card has to come from the remaining 48 cards. Right? You've used up 4, that leaves you 48 left, and I need just 1 of those for my last spot. Right? That is the probability of getting 4 of a kind. Right? This is pick the 5th card. The 13, Jacob, is the this right here. Picking one of those numbers or letters, right? So it's you know, which one do you want to have? Do you want to have the ace, the 2, the 3, the 4, the 5, the 6, the 7, 8, 9, 10, the jack, queen, or king? You have those 13 options. +4, +1.
Isn't like the second number in the combination thing, like you picking one card? So you picking a certain amount of cards, so 1 and 4 and 1.
So in like the first one in the 13, choose 1. It's you have 13 options.
Mm-hmm.
You're picking one of those options. So you have 13 values of the cards. You're picking one of those values.
Okay.
That is done in there. You have 13 ways to do that.
Okay.
That make more sense?
I guess.
So like, do you see where the 13 is coming from?
Yeah, 13 different suits, or 13
Mhm.
different numbers.
Yeah, and that value C13(1) is 13,
Mm-hmm.
right? The second part, choose 4 from 4, well, you can only do that one way. So it'd be 13 times 4 times 48, choose 1, that's times 48.
Okay.
Joel, yeah, go for it. Joel, yeah, that's where the 48 comes from. Yeah, go for it, Paul.
Yeah, so I actually had a question about the second combination, the 4. Wouldn't
Yeah.
it be 4? Well, I was thinking it would maybe it'd be 4 choose 3, because when you choose the first pick a card out of 13, you already have a guaranteed suit, so you just gotta choose 3 more of that number.
The 4 choose 4 is picking your suit, right? So it's saying, do you want the heart? Do you want the diamond? Do you want the spade, or do you want the club? Right? But since this one is asking that you get 4 of a kind, well, you need all 4 of those in there. Right? So you're in a sense picking all 4 of those suits.
Can you explain what 4 of a kind means?
4 of a kind is like, so if I draw my 5 cards, right, 4 of a kind would be, let me just make the nicest one. You get 2 of hearts, 2 of diamonds, 2 of clubs, 2 of spades, and then something else. Let's just say 10 of hearts.
Okay.
You get those 4 2s in there.
Okay. Would you be like on a test? Would you be able to like give an example if you do a card thing?
Yeah, for sure. I tend to stay away from cards on exams because of this.
Okay.
Yeah. All right. So I mean, looking at this example, you know, we picked the value. So in this case, I chose 2, right? But I had 13 different options. We had to pick all 4 suits. That's the 4 choose 4. And that 5th card is coming from, well, if you think about it, you know, I had those 4 cards, right? What's that 5th card going to be? Well, I have 48 options from there, right? And this was just an example, but then you have 48. Right. Yeah, go for it.
I was just agreeing I should turn off my mic.
This comes out to be really small, which you know it should be really small because this is really hard to do. This comes out to be, you don't have to multiply it out, but just so you can see it, 0.00024, but I think there's more decimals after, but it's about that value, which is really small. All right, any other questions on that one? The percent, you can just leave it as a decimal. That percent is 0.024%. Just moving the decimal place over to the right. Twice. All right, why don't you guys go take 10 minutes then. If you want, you can try this next example while you're waiting here. We'll go take 10 minutes and then we'll come back and do the rest. Ask questions if you have questions. Karima, so the videos actually I checked the other day is I'm not getting the videos back from Zoom. So I would say just look at the notes. But Lev said actually he would post the videos on YouTube. Lev, can you put that link again in the chat, and I'm gonna post it to our Canvas page. Cool, thanks. Yeah, so 3 of a kind is pretty much set up the same way. The things that change are you still got to pick the card, right? 13, choose one. The suits change a little bit, right? Because now you're only choosing 3 of the suits. So you got the 4, choose 3. Then you got to choose the last 2 cards. I'm checking yours, Willie. You did a little bit differently than me. That's a 13, 4. 12, choose 1. Oh, you're doing, Willie, you're doing the next example, right? Okay, I thought you were just doing, okay, yeah, I read your thing wrong. I thought you were just doing just 3 of a kind, like a separate problem. Yeah, you're good.
Professor?
All right, so just posted the Zoom link and the YouTube page on Canvas. If you go onto Canvas, I think even if you just are like on the homepage, there's like a drop down that says announcement, and it should be on there. So you got the YouTube link and the Zoom link on there now. I just checked these. Yeah, you should see it in there. All right. All right. So let's do the next one. Okay, so now this time 5 cards, same thing, full house. So a full house is 3 of a kind and a pair. So what that could look like is, you get 3 of a kind. So I used 2 last time. Let me use 4. So you get the 4 of hearts, 4 of diamonds, 4 of clubs, the 4 of spades, and then that's a lie. So you get something like that, and you get a pair. So let's say 10 of hearts and 10 of diamonds. Okay, so you get a pair and then 3 of a kind. Okay, so what happens here? Okay, well, we're still dividing by the same sample space, right? The way to choose 5 cards. Right, so now the difference here is that, I got to pick the value to be the 3 of a kind, and I have to pick the value to be the pair. Right, so let's choose the value to be the 3 of a kind. Well, okay, so that is, I have 13 different values. All right, I need to pick one of those to be the 3 of a kind.
So why is it 1 and not 3?
Because this is picking the value. Or I'm picking the value of the card. So either ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, or king. Or picking the value. The 3 is going to come from, well, I have 4 suits to choose from. Right, I got hearts, diamonds, clubs, and spades. I need to choose 3 of those. Right, you see how I only had 3 in here? Right, I got to choose 4 of those 3. So this is picking the suit. Okay, so we've picked our first 3, the 3 of a kind. Now I got to pick the last 2. Okay, so first off, I got to pick the value of this card, right? Well, I used up a value over here, right? I don't want that same value because that changes it. Okay, so now instead of having 13 values to choose from, I actually only have 12 values. I got to pick one of those. Right, so let's say we decided that the second value is going to be the 10, like how I have it here, right? Well, there's 4 10s to choose from, right? And I need 2 of those. All right, any questions on that? Yeah, it's because it's 12 because one of those values goes away because you chose for the first 3. So like in the way I drew it, we had the 4s in the beginning. Well, to pick that second pair, I don't want to pick a 4, right? So you got to get rid of that option. So that leaves you with 12 options left.
if that last card was going to be not a number other than 10, would we multiply it by something different from 4 choose 2?
So like, I mean, that's just an example. So I mean, this right here, what we have is the general one that applies to any of them. This is just helping us look at like building it. Right, so this is saying it can be anything, right? It doesn't have to be the 10. Right, this right here is giving me the options for it to be anything. So this value, if you were to, multiply it out, 0.00144056. All right, any questions? You can literally do all the poker hands if you want. Some of them get kind of tricky. 3 of a kind is a little bit tricky. You got to think about that one. But, if we have time, I can do it. All right, any questions on this one? All right, so a little bit different of an example. So if I draw 5 cards, one by one, what is the probability that I draw the 2 of diamonds, 3 of hearts, the queen of spades, the king of hearts, and the 4 of clubs in that order? Okay, in that order, if part A, the card is not put back after each card is dealt. Okay, so it's like I give you a card, you keep it. I give you another card, you keep it. I give you a third card, you keep it. Give you a fourth card, you keep it. Give you a fifth card, you keep it. And I want those cards in that order. Part B is the card is put back after each card is dealt. So I give you a card, you look at it and you give it back to me. And then I give you another card, and then you look at it and give it back to me, and so on. Okay, these are a little bit different. Okay, so let's talk about our denominator. What is our sample space? Does the order matter in this one, or does the order not matter?
I think it does.
It does matter, right? Because we said in that order, right? So we're saying in that specific order, the order does matter. Okay, so this isn't a combination, this is a permutation, right? Of 52 cards, and I'm picking 5 of them. All right, the order does matter in there. Okay, now think about this one in the sense that, okay, how many ways can I give you the 2 of diamonds? So the first card I want is the 2 of diamonds. How many ways can we do that? So how many 2 of diamonds are there? There's only 1, right? So you got 1. How many 3 of hearts are there? Well, there's only 1, right? The queen of spades, there's only 1. The king of hearts, there's only 1. The 4 of clubs, there's only 1. Right? In a sense, there is only one way to do that. All right, so your numerator is 1. All right, it's a little bit more than 52, Willie, because your denominator is that whole sample space of 52 choose 5. Right, that 52 choose 5, you think about it as, well, I had 52 options for the first card, 51 for the second card, 50, 49, and then 48 cards. Yeah, that's what the permutation is. So it's 1 over that big number, right? Because if you just think about this logically, right, the chances of you doing that, right, me giving you, you draw a card and you get the 2 of diamonds, and then the second card is the 3 of hearts, and then so on. Chances of you doing that is really, really small. Actually, don't. I didn't even multiply this out to see what this was. But it's something super, super small. All right. What we call this, though, is sampling without replacement, right? You're not putting that card back every time that it's dealt to you, right? The second one would be sampling with replacement because you're putting that card back every time. All right. Are there any questions on part A? So, I mean, this is your answer right here. You can multiply it out if you want. Yeah, it's something. Is that what it comes out to be, Joel? It's something super small. 3.2 e to the negative 4. So 0.00032. Oh, negative 9. So yeah. So it's a decimal, 8 zeros, and then 32. Okay. The second one. Okay, so this is going to be sampling with replacement because you're putting that card back every time, right? You're replacing it. Same idea, right? The top is going to be 1, right? There's only one way to do all that. The thing that changes is your denominator, right? Because the way I wrote this out up here, you know, you had 52 options, 51 options, then 40, then 50, then 49, 48. Well, in this case, you know, I give you your first card, you have 52 options, right? But remember, we're putting that card back. So when you put it back, you actually then again have another 52 options, right? You're putting it back, so then you get 52, 52, and 52. So this is 52 times 52, so 5 times 52 to the 5th power. And that should be even smaller than the one before. All right, are there any questions on those two there? 2.6, negative 9. So yeah, that's smaller than the previous one. Right, and it makes sense. It should be super small, right? This is definitely not a common thing to do to get the exact 5 cards that you need, right? Specifically 5 cards. Right. The other way you can think about these probabilities, I mean, is we haven't talked about like multiplication and adding probabilities, but I mean, if you think about, you know, let me just, this can be the same. So let's just do it for part A, you know, but for part A, you know, what's the probability that you draw the 2 of diamonds? Well, okay, 1 out of 52, right? Times, because you need everything, which we haven't talked about. What's the probability you get the 3 of hearts? Well, then that's 1 out of 51. Queen of spades, well, then that would be 1 out of 50. All right, king of hearts, well, then 1 out of 49, and then 1 out of 48, which is the same thing as that. Those are equal. All right, so another way to think about it. For part B, it works the same, except it's always 1 out of 52 because you're putting that card back. All right, any questions on that one? Okay, so it's not matter. No, the order matters in both of these. These are because we want them in that order. All right, in that order. All right, so for both of these, the order does matter. All right, so this next theorem is something we did in the set section. So in 2.2, right? You guys remember complement. So complements is everything that is not in that set, but still part of your, we called it our universal set. In this case, you know, we're talking about the probability of E complement. So that's everything that is still in your sample space, but not in your event E. And you know, we did that probability, or we did that before, right? So it'd be everything in U, and then we have that minus symbol, and then from everything that was like an A, right? So it's the same idea here, right? The probability of E complement happening is 1 minus, because everything has to add up to 1, the probability of E happening. Okay, so we're going to use that in these next two. Okay, so if we look at this example, what's the probability of getting at least 1 heart if you are dealt 5 cards? Okay. Now, at some point, I don't know if we've talked about the at least part, but at least 1. I know we did the password one, right? We did the password one. The complement of at least 1. You guys remember what the complement one of at least 1 was? Yeah, none. So the complement of at least 1 is none. All right, so if we do this, so instead of doing at least 1 heart, it's a little bit harder to do it that way. So we can think about this as doing this probability would be 1 minus the probability of getting no hearts from these cards. Okay, those are equal. Okay, so we do 1 minus. So what is the probability of getting no hearts? Okay, so, you know, I think the nicest way to think about this is probably the way we did it up here, right? So, I mean, how many options do we have for the first card that we get? Well, the first card, we don't want it to be a heart. So the probability of the first card not being a heart, remember there are 13 hearts, right? So get rid of those because I don't want those. So I have 52 minus 30, or 13 is a 39. Not hearts left out of 52. Right, we're doing without replacement, so we're not putting it back. Okay, so then the next one would be, well, I got 38 cards left to choose from out of a total 51, right? Because we lost a card. And then I got 37 non-heart cards left out of a possible 50. And then 36 out of a possible 49, and 35 out of a possible 48. And I didn't multiply all this out. But that is what we would have. Cool, thanks, Barry. 0.7784. All right, so why don't you guys take a second, think about the second one. So sequence of 8 bits is randomly generated. What is the probability that at least one of these bits is 0? All right, so for the second example, so you got 8 bits randomly generated. What's the probability at least one of these bits is 0? So let's look at the complement. All right, if you have at least one, look at the complement. So at least one, complement of that is none. So no zeros. Okay, so if none of those are zeros, in this context, that means that all of them are ones. Okay, so we want is 1 minus the probability of all ones. Okay, so 1 minus, so the probability of getting all ones, well, how many total different sequences do we have possible here? How many possible sequences are there? Yeah, so you can, there's only one way to do the all ones, right? It's that they're all ones. Out of a total, well, there's 2 to the 8th of them, right? Because you got 8 spots. And each one of those, you have 2 options, right? Either 0, 1, 0, 1. Right, so you got 2 to the 8th. So 1 over 2 to the 8th. This number comes out pretty nicely, I think. This should come out to 255 out of 256. Now, I don't know what that is as a decimal, but it comes out pretty nicely. .996. Thank you, Andre. 6. Okay. Any questions on that one? The last thing in this section is something we've seen already again in the set section. So you see 2 events, E1, E2, and then the probability of the union of those two happening is the probability of each one, but subtracting the probability of the intersection, right? We've seen that happen before when we were counting things in the union, right? You have to subtract away that overlap to not double count it. All right, so this example here, I like this example. Like we skipped chapter 4, so we kind of didn't really do it, but I can quickly tell you what this means. So what's the probability that a positive integer selected at random from the set of positive integers less than or equal to 100 is divisible by 2 or 5? When we talk about numbers being divisible, or a number divides another number, it means that you divide that number and you get a whole number. So no decimals, no fractions. Okay, so our two events here. So event 1 is a subset of all these. So let's say these are the ones divisible by 2. And the second says divisible by 5. Okay. So we have our two things there. Okay, we want to know what's the probability that, we pick a number and it's divisible by 2 or 5. Okay, so you have that or in there giving you the union. Okay, so the probability of E1 union E2, that's going to be equal to the probability of the first one plus the probability of the second one minus the probability of the intersection. Okay, first off, how many numbers are there to choose from total? How many total numbers are there that we're playing with? 100. It's not 101 because we're not including 0. All right, we're just looking at the positive integers. So it's 100. Okay, so all these denominators should be out of 100. There's 100 total numbers. Okay, so let's just fill those in, minus something over 100. All right, so the probability of us picking a number in the first set, so divisible by 2, how many numbers are divisible by 2? Yeah, there's 50 of them, right? It's going to be all the ones, all the evens. Okay, so there's 50 of them. Okay, how many are divisible by 5? 20, right? And the nice way of doing that, you'll see in the next section, is dividing them, right? 100 divided by 5 is 20, right? If we don't get a nice number, you'll see us in the next section take the floor function of that. But I mean, these are nice numbers, right? It's going to be, what numbers are divisible by 5? Well, it's every 5 numbers all the way up to 100. There's 20 of them. Okay. Now, how many are divisible by both, right? Because that's what that last thing says. The intersection of E1 and E2. So it has to be divisible by 2 and by 5. Right? So how many are divisible by both? Yeah, there's 10 of them. All right, where does that 10 come from? Well, if it's divisible by 2 and it's divisible by 5, then it's divisible by 10. All right? Yeah, so you're dividing by the product of those two. 100 divided by 10, well, there's 10 of them, right? 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. There's 10 of those numbers that are divisible by 10. All right, so this is 50 plus 20 minus 10. That's 60 out of 100, so 60%. Or 3/5 or 0.6, however. I don't even care if you simplify it. You shouldn't get anything greater than, Willie. If you don't subtract the overlap, you could get more than 1, which then is your problem, right? Because you're double counting numbers. Misa, the 10 comes from that intersection right there. It's the things that are in both of those sets. So it's both divisible by 2 and by 5. So it's divisible by both. It has to be divisible by 2 times 5, which is 10. And there's 10 numbers from 1 to 100 that are divisible by 10. Any other questions on that one? All right, so the last one from this section is the money hall problem. You guys, I don't know if you guys have ever seen this before. You might have, I think it comes up in the movie 21. I think his first day of class, Kevin Spacey's character, I forgot what his name was doing a lecture on probability, and this comes up. So what this problem is, there was a game show, I think it's still on, but it's called Let's Make a Deal. And what they used to do at the end was there were 3 doors. All right, door number 1, door number 2, door number 3. Okay, behind one of the doors was a prize. Behind the other 2 doors was nothing. Okay, so what it was is the host would ask the contestant to pick a door. Okay, so let's just say y'all picked number 1. Okay, so you picked door number 1. All right, and then I say, as the host, I say, okay, well, I'm going to do one thing, and I'm going to tell you it is not in door number 3. Okay, so I'll use you with door number 1, door number 2. And I ask you, by me telling you door number 3, it's not in door number 3, right? Would you like to stay with your original door? Would you like to switch? Right, those were your 2 options. And for us, right, does it matter? If we just think about probabilities, would you want to stay with door number 1, or would you want to switch to door number 2? Or does it not matter? Right, are they the same? I see one answer. What does everyone else think? I got 2 switches. I got 3, 4 switches. So someone tell me then, why at this point when door number 3 is crossed up, why do I not have a 50-50 shot anymore? Because it looks like I only have door number 1, door number 2. That looks like 50%, 50%.
Because it's still a 67% chance that it was in one of the 2 doors you didn't pick.
Yeah, right. So what happens is, if we backtrack a little bit, before we even pick a door, right, the chances of you getting it right from the very beginning are 1/3. Right, you had a 1/3 chance from the very beginning. Okay, that means that you had a 2/3 chance of not picking the prize, right? So in this story here that we picked, you had a 1/3 chance. And these 2 doors together, you had a 2/3 chance. All right, so then by me crossing this out, right, it's like these entire 2/3 kind of move into this door. Right, it's not 1/2, right? Because your original thing that you picked was 1/3, right? So in this case, right, and I always tell every time I go over this with the class is, you know, you want to switch. Right, based on probability. Now, if you're like really superstitious and, you know, number 1 is your favorite number and it's always lucky to you, totally up to you. Right. I'd say if you ever get on a game show like this and you switch and you get it wrong, that's my bad, I guess. But that's just probabilities, right? It's 2/3 to 1/3. Right? It's not 100% certain that you're gonna get it right. You have a better shot, right? It's actually double. So I think, you know, that's always a cool problem to do at the end of a probability section. Okay. Another way to think about it is, you know, if it went up from 3 doors to like 10 doors, right? You had 10 doors, and from the very beginning, you know, you had to pick one. Well, the chances of you getting right are a lot smaller now, right? So let's say you pick door number 2, and I knock out a bunch of other doors, but you would definitely switch in that situation, right? Or even exaggerate it more if there were like 100 doors, right? The chances of you getting right from the beginning are a lot lower. All right, any questions on that one? I'm gonna stop there. I do have office hour right now. Actually, so I told you guys I was gonna write this out again. So for your exam, so this is Wednesday. Okay, we're looking at chapters 2.3, 2.4, 2.5. Okay, so the last stuff in chapter 2. We're looking at 3.1, 3.2, 3.3. All right, algorithms. I would say, you know, with these sections, because this, you know, the end of chapter 2 and the chapter 3 stuff. Chapter 2 was a while ago. Chapter 3 is where we switched to online. So I know I got a little messy. I'd say if you're looking for content on like what would show up on the exam, look at the quizzes. Okay. So just look at the quiz that you had for those sections. And then we had chapter 5, so 5.1 and 5.3. And then from chapter 6, 6.1, 6.2, 6.3. So, you know, as you're going through your homework from those 3 sections, you'll see that it all just kind of blends in together, right, with those types of problems. Same with 5.1 and 5.3. Okay, so I would say, you know, don't really think about this as 3, 6, 7, 8, 9, 10, 11 different sections, right? A lot of these are blended together. All right, so remember, let me just show you guys one more time. Let me wait until you guys write that down. But remember, the way this is going to happen is Wednesday, 12:30. Your test will be available on Canvas. All right, you're going to go hit on the thing that says Exam 2. And there'll be a little download link right there that says Exam 2 PDF. All right, you download that. Do your work on paper. You know, please keep that neat and organized. You know, don't try to, you know what I mean. I had you guys do this on paper before, so you guys are fine. And then when you're done, you're gonna upload it to Canvas just like you did with your quizzes. Okay, so, and like I said, please upload as a PDF or a JPEG. Otherwise, I can't write on it. And if you want to make it easier for yourself, rather than uploading 6 different, 7 different like files, just download a scanner app, and it usually just makes everything into one file, and you can just upload it that way. Which I know some of you have used that because I've seen you guys turn it in as PDFs, which is nice, and as one file. All right. Any questions on exam stuff? So the one I use, Willie, is a Genius Scan. So I'm gonna send you guys the message with all this stuff again after, and I'll put that in there. I'll put you know, if there's a bunch of different ones you can probably use. I just use Genius Scan. I think it's the easiest one for me to like upload. So I just usually just email it to myself and do it that way. I know there's a way to do it through like the Canvas app, but I don't know if that comes up as different files.